capturing autonomy features for unmanned spacecraft.
Good morning, everyone. So basically, this presentation will outline joint research, the results of a joint research work between LIRO, the Irish Software Engineering Research Center, and the ASTIC division of the European Space Agency in the Netherlands. Basically, actually, this project was on methods and tools for onboard software engineering, and it had 4 work packages, and the presentation actually is based on this second work package, which was on autonomy requirements engineering. So basically, my talk will start with a short introduction to the problem domain, which is kind of required background for the rest of the slides. And then I will outline the difference between automation and autonomy, and we'll say a few words about the different levels of autonomy considered by the European Space Agency for unmanned missions. Then in more details, I will talk about the autonomy requirements engineering. This is the approach we developed for this particular project, and this is going to be followed by a case study. It's a proof of concept case study where we apply this autonomy requirements engineering to the BP Colombo mission. And the talk will be concluded with short summary and some future work remarks. So basically, you all know here, you're NASA people, that both NASA, ESA, JAXA, and other space agencies, they're approaching, well, the problem of deep space exploration by relying on unmanned spacecraft. Basically, the idea there is to increase the amount of science by allowing the spacecraft perform autonomously without human intervention. And the promotion of autonomy in space missions, however, appears to be quite challenging task. And well, one of the solutions NASA and ESA are currently approaching is the so-called autonomy computing paradigm. This paradigm, well, was initially announced in 2001 by Paul Horn, a chief scientist at IBM, who linked actually a human autonomic nervous system from the human body to computerized systems. Well, realizing that computerized systems can behave like the human body's autonomic nervous system, I mean, unconsciously react to changes in the environment or the system itself. Well, the problem with this autonomy computing paradigm is that today, whatever well, we intend to do with this paradigm to develop systems, well, coping with this paradigm, we use the traditional software engineering approaches, but they're not very appropriate for that. Well, simply they pay scant attention to these autonomic features. And one of the biggest issues, actually, that the NASA and ESA engineers is that they don't realize the difference between automatic and autonomic. And you see this is not the same. So in this particular, well, project, well, we dealt with the first challenge, which is the recitation and expression of the so-called autonomy requirements. And basically, the idea was how to determine the so-called autonomic features that need to be developed in order to come up with autonomous spacecraft. And basically, our target was the ability of an approach that will generate autonomy requirements supporting these features. So, as I mentioned, one of the biggest issues is that software engineers don't really differentiate between automation and autonomy. So I say a few words about it. Basically, both notions mean processes that where human activities are replaced by computer systems. Well, but when the processes are automated, basically what we have is a kind of straightforward replacement where we have step-by-step sequence of activities replaced um, by by the machine. So instead of having a human operator performing these activities, we have a computer performing this step-by-step sequence of operations. When we talk about autonomous processes, however, we have something more challenging there. We have kind of more ambitious goal there, where actually we don't really replace, not only replace the activity, but also we replace the thinking. I mean, it's like emulation of the human process. So often, complete autonomy is not desirable, just because we don't really trust the technology today, and human intervention sometimes is really necessary just to reduce the risk of failure. So that's why we need to deal with so-called adjustable autonomy, where actually both human intervention and autonomy must coexist when we control, for example, the operations on spacecraft and so on. So definitely autonomy should be adjustable in such a case, and we can deal with complete, partial, or no autonomy, which is another issue when it comes to autonomy requirements engineering. These today consider 4 levels of autonomy, as you can see here, E1, E2, E3, and E4. Basically, the first 2 levels, E1, E2, are more or less automation. So E3 and E4 are real autonomy. That's the levels we were targeting with this autonomy requirements engineering. So all the missions today that pretend to be autonomous missions are actually are targeting the E3 level of autonomy. So they target this level of autonomy. It's kind of event-based autonomy where the operations are, any operation on board is triggered by events that are realized, raised in the system itself or in the operational environment, for example, the space. Outside, the E4 level of autonomy is the ultimate level of autonomy. It's goal-oriented. We call it goal-oriented level of autonomy. So once achieved, this level will allow the systems, the unmanned spacecraft, for example, to perform like human beings. They should be able to follow their goals, mission goals, and adapt to the changes in the environment and to, some problems in the system itself in order to pursue their goals. So this is, as I said, ultimate level of autonomy, and this is what we're planning for the near future. So the first question was where to start from. When we started this project, actually, we realized, we knew the nature of the self-adaptive systems. Actually, the autonomic systems are self-adaptive systems, where basically we observe these things. Any self-adaptive systems is able to autonomously pursue goals. It's able also to monitor environment and subsystems, part of the system, and eventually modify its behavior, and why not structure, internal structure, according to the changes in the operational environment and goals. So that was the starting point in our research, and it helped us actually come up with a solution where we use the so-called goal-oriented requirements engineering to elicit and define special system goals, and then we apply in each one of these goals the so-called generic autonomy requirements. This is a mechanism we develop in the course of this project, where actually the basic idea is to derive for each goal, actually, for each system goal, we derive and define assistive and often alternative goals, which we call self-objectives. These self-objectives help the system pursue its initial goals in the presence of factors threatening the achievement of these goals. So if there is a problem, for example, and the goal cannot be achieved, the initial goal cannot be achieved, like just transporting the spacecraft from point A to point B, then there will be a few self-objectives supporting this goal in the presence of particular problem. One of these self-objectives will be, the system can shift to one of these self-objectives just to fix the problem and then continue with the initial goal. In our approach, actually, as I mentioned, we basically merge the goal-oriented requirements engineering with the generic autonomy requirements approach to produce goals. new goals for the system. And in the last phase of this approach, actually, we specify these requirements with special language, which is NoLang. I'll say a few words about it. This is the language that codes quite well, and it's still under development. It's a language we're developing currently at Liro as part of another project, but we're at the last year of the project, so it's quite advanced there. Well, with this language, actually, we specify the requirements in formal way, so we can basically we end up with a model, and we can you see what we can do. Actually, we can test, we can well just verify the model to some extent. I'm not saying that that's quite perfect, but it works. Okay, this is the autonomy requirements engineering. Well, basically, as I mentioned, at the first stage, we derive the goals of the system. So we built goals models, and then actually for each system goal, well, often actually a goal comes with some constraints. So with a goal and associated constraints, for each goal and associated constraints, we apply the generic autonomy requirements model, where actually we consider requirements, generic requirements in terms of autonomicity, what knowledge should be given to the system in order to deal with particular constraints, for example, awareness requirements, monitoring requirements, requirements related to, well, quality of the system, like adaptability, for example, dynamicity, robustness, resilience, and mobility. And after the analysis stage, analysis process here, we derive the system goal, the original goal, system goal, but as I mentioned in the previous slide, well, supported by assistive goals, which we call self-objectives. So you can see here, this system goal is supported by 5 self-objectives. And also for each one of these self-objectives, we derive concrete version of the autonomy assistive of the generic autonomy requirements, which we call autonomy assistive requirements. So now knowledge has a more concrete meaning in terms of what you need to know in order to achieve this self-objective, or this one, or this one. The same for awareness, monitoring, and so on. So in the course of this project, we developed generic autonomy requirements models for the different classes of space missions. So basically, we consider 2 major classes: Earth orbiting missions and interplanetary missions. And for Earth orbiting missions, actually, we derived generic autonomy requirements for the subclasses like polar low Earth orbit, satellite constellation missions, and so on. The same for interplanetary missions like small object missions, missions using low trusted trajectories, and so on. So basically, for each one of these missions here, I mean classes of missions, we have a generic autonomy requirements model. And when we develop requirements, autonomy requirements, I mean, when we apply the autonomy requirements engineering, the first thing is to realize what mission is this. For example, if it's for low Earth orbit mission, then we apply the generic autonomy requirements model we built for this particular mission to come up with the self-objectives required by this mission, these classes of mission. So this is the same thing, but I mean graphically represented here. So basically, as I mentioned, for each model, and we get the goals and the constraints associated with goals, and we merge these goals with the generic autonomy requirements. But also, actually, if we have on place something like space mission analysis and design, this is one of the stages actually usually the software engineers preparing space missions need to perform. So if you have this in place, you also can merge with this analysis process. So basically these additional requirements are coming from this space mission analysis and self-objectives, space mission analysis and design phase actually. They allow us to derive new requirements. I mean, again, at the end, we get the same thing. We get knowledge, awareness, monitoring, plus self-objectives, but these are more, how can I say, these self-objectives are more relevant or richer in terms of that now we also can consider mission duration, for example, availability, survivability, mission utility. These things actually coming with the space mission analysis and design. So in addition to that, we also may consider the different hazards, actually, the safety requirements. So basically, we can use different hazards to identify self-objectives with associated attributes required by these self-objectives. And in this particular process, I mean, if we apply this, we need to follow maybe something like this. Like the first stage is to identify the hazards, and then to analyze these hazards, like what are the possible causes of the system hazards, and then to identify safety capabilities that need to be provided for the system in order to deal with these hazards. And actually, the requirements, the autonomy requirements derived from these hazards come in terms of safety requirements that either prevent the hazards to occur or to mitigate the results that accidentally occur by implementing self-objectives that deal with these hazards. So once we identify the goals and once we apply to each goal, actually the generic autonomy requirements to come up with self-objectives, we need to record this. And we record these self-objectives with this associated attributes, autonomic attributes, in terms, in the form of the so-called autonomy requirements chunks, where actually basically we, to each goal, we attach a scenario. Often we have multiple scenarios that can be attached to a goal. And we combine these scenarios with together by using and or relationships. Well, as you see here, actually, as I mentioned in one of the previous slides, basically, in one of the final steps, after we come up with the chunks, we need to formally specify these autonomy requirements chunks, and for this we use non-lang. Non-lang is good for that because it allows us to specify the self-objectives as special policies, where we consider goals, situations, and actions. Basically, the actions are present the functionality of the system of the unmanned spacecraft, for example, and in top of that, actually, to realize how when we need to consider these self-objectives, when the system needs these self-objectives when the system needs to shift to these self-objectives, actually, we consider special situations, which we also determine and specify with non-lang. So basically, we have policies and situations related together where the situations present the self-objectives. Actually, you'll see quite soon this as an example. This is a formal specification of a policy where we use non-lang. Each policy has a goal. It's quite, as I said, non-lang is very appropriate because it deals with goals. So this goal is the mission goal, one of the goals a mission must pursue, for example. And these are the situations, for example, here, although there is only one situation listed here, that will trigger shifting to alternative goal. I mean, to self-objective that will help the system pursue the original goal in the presence of some hazards, for example. And also in this particular specification here, it's quite a little snippet here. You can see, well, some particular sections here where actually we map conditions, particular conditions to actions. The actions, as I mentioned, present the functionality of the system. So remember that this is, we deal with the requirements engineering approach now. I mean, it's not the implementation of the system yet, but usually at this stage you outline the functionality of the system, and even if you deal with system that's being implemented already, you can say that you need more functionality. So, I mean, you're not really bound to the functionality if it's there. I mean, to the already implemented functionality, because as I mentioned, this is requirements engineering. You must actually come up with a solution to problems that, and this is that actually deal with autonomy, with the system autonomy, and often the functionality presented, for example, or invented present is not enough, so you need to deal with something extra. I mean, you can invent new functionality here. Although, as you can see, these are quite simple functions here, like shade instrument, start cooling system, go to polar orbit. As I mentioned, sometimes you may require a new functionality. So the case study, at the beginning I mentioned that in this project we needed proof of concept case study, and our proof of concept case study was Baby Colombo. Baby Colombo is a manned mission, well, expected to launch to Mercury in 2015. It's a joint project between the European Space Agency and JAXA. Well, basically, it's composed of two orbiters, as you can see, the Mercury Planetary Orbiter and Mercury Magnetospheric Orbiter. So from Earth to Mercury, they travel together, and then they separate and are supposed to perform some experimental experiments there, scientific experiments. So in our particular work, actually, we applied the autonomy requirements engineering approach, and we derived the goals of the system. They're missing. Anyway, there was supposed to be, it's maybe my mistake, something like a class diagram when all these goals are hierarchically organized. So let's suppose that we have this diagram here. Sorry for that. And here you can see three of these goals, actually transfer objective goal, orbit placement objective goal, and scientific objectives. So basically these are three classes of goals. In our particular case study, let's say for each one of these classes of goals, transfer objective, orbit placement objective, and scientific objectives, we derive the self-objectives of the system. So how we did that, as I mentioned, for each system goal, let's take the transfer objective goal, we applied the generic autonomy requirements, and we came up with, for example, self-requirements, like, for example, for the orbit placement objective, self-jettison is a self-requirement, self-capture is another self-requirement, self-escape, self-thermal control. Let's see one of these, like self-capture. As you see, it's a plain English here, so it says that the composite module shall autonomously determine a steering claw and use law truths to achieve capture around Mercury. So these are the self-objectives that are supposed to assist the orbit placement objective. This is one of the mission goals here. And in addition to this, if you remember, the generic autonomy requirements model actually comes with additional properties like knowledge, for example. We determine the knowledge requirements required that need to be fulfilled in order to have these self-objectives actually achieved. So, for example, as I mentioned, self-capture, self-objective, we require knowledge like center force field physics, steering column model for weak stability boundary capture, and so on. So this is the knowledge that required by the system in order to be able to perform the self-objectives defined with the autonomy requirements in generic approach. All the requirements, awareness, for example, what kind of awareness we need in order to have self-objectives like capture awareness, mercury escape awareness, trajectory velocity awareness. Another requirement is the monitoring requirement. What should be monitored by the spacecraft, for example, the environment around Mercury, the sun, the plant operations. Other requirements, the adaptability requirements, dynamicity, robustness, resilience, mobility, so all these are coming from the generic autonomy requirements model. For example, resilience, as you can see, both spacecraft modules must be resilient to magnetic field changes. So this comes from the analysis phase of the autonomy requirements engineering approach. I don't know why all these pictures are missing. Actually, here, we wait a second. Do you need to close this?
Is that the one you're looking for?
Yes.
Okay, let's see about this. Okay. Apologize.
No problem. Anyway, so as you can see the diagram here, well, basically, this diagram presents one goal here, orbit placement goal. Here, it's a system goal, and it's surrounded by the self-objectives, well, derived by the autonomy requirements engineering approach. So you can see self-jettison. There are, for example, two self-jettison objectives, and these are the actors. Well, this is a graphical presentation of this particular solution here, but I don't know if it's quite, if you can see, but basically the system shifts two different self-objectives, and because most of them, they inherit the original objective, the original goal, orbit placement goal. So when it shifts to this self-jettison one, for example, self-objective, the system preserves the original goal, which is actually orbit placement of the two orbiters. So this is the global view, actually, where we take one particular system goal and present it together with all the derived self-objectives. And for each one of these self-objectives, actually, we have the different autonomy requirements in terms of knowledge, adaptability, resilience, and so on. And you can see one requirement chunk here for the self-protection, one self-objective. So it has assisting system goals. So basically, this is the goal that's assisted by the self-objective. It's called BP column transfer objectives, the actors there, and the targets. So, and there is, as I mentioned, in each chunk we have scenarios, and there is one scenario saying what the system is supposed to do in order to avoid, and in order to deal with a particular problem. In this case, when there is a presence of high solar radiation, and the spacecraft must be protected. So, once we define all the self-objectives and the requirements chunks associated with the self-objectives, along with the generic autonomy requirements associated with self-objective, we apply the null to specify formally these self-objectives. And as I mentioned, for this we use policies and situations and actions. So null is a knowledge representation language. This is something very important here. So basically we build a model of the brain of the system, and because null comes with a particular reasoner, so basically we can implement this reasoner in the system itself and operate on this model. So that's why we start with domain-relevant concepts and objects when we build this model, which present the dictionary, basically, of the brain. I mean, all these terms here are expressed in terms, or expressed as concepts. For example, this is the MMO, one of the spacecraft, elements, for example. And you can see this is a tree representing the concept model of this spacecraft element here, where we distinguish different entities. Like instruments, for example, magnetometer, nutation, damper, and so on. So basically, this concept presents, this structure here presents the brain, and each one of these concepts is specified like this. You can see with properties, functions, and this is very important, states. So for not all of them, but for some of the important concepts here, for example, some of these important concepts here, usually at the leaves, at the end of the concept tree, actually, we specify states. These states allow actually the system, the reasoner itself, to determine at runtime was the situation, was the current state of the system, or was the current state of the environment, and then to map situations, for example, to policies. And you can see, for example, Emil spacecraft here is a concept, part of this tree, somewhere here, Emil spacecraft. Anyway, it's there. So the MMO spacecraft is specified these particular states: orbiting, in transfer, in orbit placement, in jettison, and so on. So all these states actually specified as Boolean expressions over the entire model, over the entire ontology. And these are the functionality that actually we give to the spacecraft in order to achieve some particular self-objectives, like move to polar orbit, wait for instructions from Earth, and so on. So, as I mentioned, actually, basically the self-objectives are specified in terms of policies, where we mapped actually a system goal, for example, to a particular situation, and to realize what situation is. In what situation the spacecraft is currently in. We, the reasoner is using the evaluation of the states. So that's why the states are important, if I remember. If you remember, here we specify states for most of the concepts here. And basically, when we specify a policy, actually we map situations to actions that must be taken by the system or realized by the system in the environment or in the system itself in the presence of particular problems. That's why we use conditions here. For example, if the solar radiation is less than 90 or bigger than 90 and so on, you can do this and this and this. On top of that, actually, we use probability distribution among the actions here, which makes the entire specification knowledge-oriented, because based on reinforcement learning ability given to the knowledge model, actually the reasoner can adapt this knowledge model to the changes, actually each one to the changes in the system or in the environment anytime when a policy is realized in terms of actions realized, well, executed by the system. Actually, the reasoner knows the success rate. So if the success rate is good, then actually this probability can either preserve its value or go up. So basically, we give with this probability race, we give our preferences at design time in terms of what actions should be undertaken in the presence of particular problems. So basically, we can have multiple options there, which is the case here, and we give our preferences. But the system learns on the fly which one of these preferences actually is supposed to be our highest preference, just because if the execution of this action, for example, move spacecraft up, is not successful, I mean, the radiation is still high, then next time, because the system is still in this situation, the system will try to move the spacecraft down, or it will do something else. So basically, the probability rates change on the fly. So on top of that, we use a particular non-long reward function, which gives the system full ability to compute the next actions. So instead of saying, okay, the next possible action should be this, or chain of actions should be this, we can say, okay, generate the next actions, which means that the system evaluates all the previous experience and come up with the most appropriate actions according to the system evaluation. So it comes in terms of special rewards associated to the actions and actually to the goals of the system and so on. So in terms of monitoring, this is how we specify the monitoring requirements. So we specify metrics. Here you can see this metric is environment metric, so we use metric resource and special values. So by specifying metrics, basically we abstract the sensors of the system, like motion detectors, like light detectors, and so on, like radiation detectors. So they operate, actually they can be used to specify, for example, situations. The awareness requirement actually is handled by the non-long reasoner. So basically, as I mentioned, with non-long we built a model of the brain of the system. Actually, basically, we built all these self-objectives are presented as policies inside, and the system reacts to changes in the environment by triggering, like, let's say, different actions handled by different, well, by triggering, by shifting to self-objectives that trigger different actions. So, and this is something that can be described as context awareness, because the system realizes the current situation, and also it can, let's say, predict the possible output of the actions that can be undertaken by the system itself in order to, let's say, help the system go out of a dangerous situation, like high radiation, for example. So the other requirements like resilience, robustness, mobility, dynamicity, and adaptability are specified in similar way, but as soft goals. So unlike the regular goals, in our approach, the soft goals have some kind of degree of satisfaction. And our work in this particular aspect of the problem is not quite advanced. I mean, we still have to do something there because the evaluation of the achievement of soft goals is not that easy. As you mentioned, we need to give to each one of the soft goals a particular degree of satisfaction, some percentage of, and it's hard to measure goals, definitely. So basically, this is the end of my talk. I realize it's quite complex, all this stuff I presented today. Basically, what we achieved with this project is a new autonomy requirements engineering approach. By the way, we published a book with Mike Hinch. The book is on sale on Amazon. It presents all this stuff there. I mean, all this research, including the case study. So basically, in this particular engineering approach, we merge the goal-oriented requirements engineering with a special mechanism which we call generic autonomy requirements that gives us the generic autonomy requirements per class of mission. So, and the result of this merge is a set of self-objectives promoting autonomicity in the system behavior. So each one of these self-objectives is intended to serve one of the system objectives derived by the goal-oriented requirements engineering. So in order to come up with a real model, because at the first phase we simply write down the requirements in the form of requirements chunks, which is actually a constructed version of the requirements in plain English. I mean, requirements associated with actors and scenarios. So in order to come up with a more realistic, or I can say manageable model, we specified these requirements chunks with the non-lang language, which helps us come up with a real presentation of the problem domain in terms of policies, concepts, situations, and also because no one comes with a reasoner, we can really test this in a test bed, for example, where we simulate the problems. So in this particular case, we use the BP Colombo mission as a proof of concept case study. So our future work is mainly concerned with new efficient tools supporting the autonomy requirements engineering. So, well, one of the first problems we need to deal with is the autonomy requirements validation, definitely. As I mentioned, although we have something like testbed, it's quite, how can I say, it's just something that we built on the scratch. So we need to work on that to come up with a real testbed where we can test the autonomy requirements. Well, basically the autonomy behavior and awareness capability of the system under simulated conditions. So we need a real test environment where we can deploy the knowledge models along with the no-lang reasoner and test these knowledge models under simulated conditions. So on top of that, we are planning to develop a kind of intelligent generic autonomy requirements framework by using special adaptation patterns. Also, we need to integrate tools handling the system analysis, system mission analysis and design approach, which, if you remember, actually adds on the autonomy requirements engineering approach by adding new requirements there that help us derive more relevant self-objectives. And also, basically, the ultimate goal of this approach is to allow for smooth transition from requirements to implementation. So one of the possible ways is to to provide facility for test case generation and code generation based on the knowledge models built with NOLAC. So this is it. Thank you very much for your patience. Yes, the answer is definitely yes. Actually, NOLAC is part of, well, it's been developed, and as I mentioned, it's still under development, but we're the fourth year of the project as part of another project of ours. It's called ASENS. It's supported by the FP7 framework. It's a European Union framework as well. And we have three different case studies there. One of them is e-mobility. So where this approach is applied to electrical cars. Another case study is swarm robotics. Although we deal with little robot environment, this case study is not that well developed. I mean, most of the time we deal with simulators. And another case study is scientific cloud. So basically this approach is applied to cloud computing. So everywhere where basically we need self-adaptation, we can rely on this. But well, because the project originally was initiated by ESA, that's why this talk is on unmanned spacecraft, capturing autonomy requirements for unmanned spacecraft. But just to maybe give you more idea about the whole thing, as I mentioned, indeed, one of the biggest issues is trustworthy. So because definitely science is not that advanced, especially when it comes to expensive hardware. So that's why we need to deal with adjustable autonomy. And this is one of the issues we deal here with this particular approach. But the biggest, maybe I can say, advantage of this is to have the test bed. So before deploying anything, you need to be able to test it thoroughly. So, and the test bed is something that, although we have a little test bed, we need to develop a very powerful test bed where you can really simulate the conditions there. I mean, the non-deterministic conditions of the environment. And based on that, and I'll come up with better solutions. Okay.
This was just in reference to your 4-stage slide where you had outlined, I guess, some safety hazards, and you did a requirements deviation.
Right.
Okay, I just want to make sure I'm clear. So you took the requirements, you looked at your safety hazards, you did like a risk assessment, and then a mitigation, and then your deviation is the result of the risk mitigation?
Right.
Okay.
Yes. I cannot find it, but yes.
That's okay. I just wanted to make
Risk
sure I followed the
assessment,
flow.
yes.
Yeah.
Yeah.
Okay, good. And then you worked that back up, and when you did your testing, you traced back to the original as well as the deviation as well.
Well, actually, the risk assessment, well, it depends on the case study. I mean,
I'm talking about the deviation portion. When you got your final requirement deviation, you
Right.
worked that back.
So tracing the requirements back, that's
Yes.
your question.
And you traced to your deviations as well.
Yes, that's
Okay.
absolutely possible. It's
Okay.
part of it. But test case generation, I mean, that's something that can help you. Let's say test exactly these requirements is not part of it. I mean, it's not being developed. But if you know what you're testing, for example, you can simulate the conditions, the basic conditions that will help you come up with a situation where you have the similar risks, for example.
Oh, okay.
Yeah.
Okay,
Similar
great.
risks.
Thank you. I just wanted to make sure I thought I had it, and I said, let me just check
No,
with
we
him
don't
just to be sure.
do any automatic analysis yet. No. I mean, that's pure, I can say, that's why we need, as I mentioned, some kind of intelligent autonomy requirements engineering environment. When on top of all this, I mean, process, we can also use patterns, for example, that will help us identify some, well, kind of recommended behavior, or in terms of, as you mentioned, when particular hazards are present, something like this.
Okay, great. Thank you.
Okay. Thank you.